Ohm's law is the fundamental equation of electronics that relates voltage, current, and resistance. Joule's law, as applied in electronics, is a fundamental equation that relates all of that to power. And if you add in Kirchhoff's laws, the voltage law and current law, the set is complete. And all of the math you will ever need to know for simple circuit building is at your fingertips. For more advanced topics such as induction and capacitance, of course, you'll need more. But to just build circuits and test them from known designs, this is all you'll ever need. And the best part is that Kirchhoff's laws are actually the easiest to understand of all of them. Let's start with a simple circuit. We have a power source, a resistor, and an LED. The resistor is to control the current through the LED to control its brightness. Now, one thing to point out about circuits before we begin. You'll notice that we have wires, and we don't really worry about how long they are, what they're made of, how they're physically arranged. We don't worry about what the resistor's made of. We don't worry about its condition. We make all kinds of approximations that are just perfectly fine for normal things. This resistor is going to be somewhere between 300 and 1,000 ohms, depending on what your LED's color is and how bright you want it, as well as how much input voltage you have. Whereas the resistance of these wires is going to be less than 1 ohm. We're not worried about the capacitance between wires. We're not worried about signal interference nearby. We're not worried about the crazy random bouncing of all of the electrons all over the place. This is a component model of electronics that's nice and simple and works 99.99999% of the time. When you have super high frequency, high tolerance applications like gigabit Ethernet or life-saving medical equipment such as heart-lung bypass machines or whatever, you have to operate with much more extreme tolerances, engineering principles, and so forth. But for the rest of us and the rest of the time, this is perfectly fine. Kirchhoff's laws are based on this component model that we use all the time. Kirchhoff's voltage law is about loops. Start at a point. Go around, back to that point. That is a closed loop. The point is that you started somewhere, you kept on going, you didn't double back or wiggle at all. You just started and finished at the same point. That's what a closed loop means. Now let's talk about voltage changes. Let's say that this is a 5-volt power supply. So that is 5 volts. Let's say that this ends up having a 3-volt forward voltage drop. That's how LEDs work. That's how diodes work. They have a forward voltage drop. Let's say this one's 3 volts. So, as you might expect, this will be 2. This is our only power supply, so we have to have a balance there. And that's exactly what Kirchhoff's law of voltage says. Now let's label the current. That's the direction the current is flowing the way we draw it. Of course, the electrons are going the other way. Don't worry about that. This is the way the positive current is flowing, the conceptual current. Now, one thing to point out about this math, we're going to be working with currents. And sometimes you don't know what the currents are. That's the point. We're using math to figure out things we don't know from things we do know. If, keep in mind this throughout the whole thing, if you ever get the arrows wrong, everything will still work. You will still get math that works out just fine. But when you calculate your currents, they'll be negative. The ones that are wrong will be negative. So all you have to do then is, after you do your math and check your math, is go back to your diagram anywhere you got a negative current and flip it. Now remember, the current's going to be the same through all here. If you have a continuous wire, no junctions, it's not a junction, just one wire, the current is the same throughout the whole wire. So whatever this current is, it's going the same way everywhere. It's the same amount everywhere. Now this is a voltage increase. If we're going in the direction of the current, right? I've labeled the current this way. If we're going in the direction of the current, this is a 5-volt increase, right? Because the negative end is 0 and the positive end is 5. Then over here, the resistor, we don't know what it is. Let's label it V2. Let's say V1 is that. Let's say V3 is that. Because we know those two, but we don't know this one. So let's say this, but it's a voltage drop. No matter which way you go across the resistor, it's going to drop. So in this direction, Remember, it's important. In this direction, it's a drop. And then over here, the current is going from the positive to negative end of the LED, because otherwise the LED wouldn't work, or it would catch fire and explode. So we're going in the correct direction. So this is also a negative because we're dropping 3 volts. They're being, quote unquote, used up. So what does Kirchhoff's voltage law say? In any closed loop, for any closed loop, add the voltage changes and it equals 0. So we have V1, which is positive, plus V2 is negative, plus negative V3 is 0. So let's plug some numbers in. 5 volts plus negative V2, we don't know what, plus negative V2 is minus V2, plus negative 3 volts is minus 3 volts, equals 0. So let's add the V2 over. We get 5 minus 3 equals V2. 5 minus 3 is 2. We just move the V2 over using simple algebra. It's all simple algebra. So that is how you can use the voltage law to figure out voltages you don't know. Draw a loop including voltages you know or can calculate and the one you need to figure out, and then do your algebra. Now, if you have a huge, crazy circuit and all kinds of voltages and currents and stuff, then you have to do matrices and linear algebra and so forth. Or you don't actually have to do that. That's just the good way to do it. You can also do it the slow way by hand very, very painstakingly. A much better idea is to find an online or commercial circuit simulator and just use that. But this is great for when you're trying to do things like, I want this LED a certain brightness. How much voltage do I need across this resistor? And using Ohm's law, V equals IR, we know the current, we know the voltage, which means we know the resistor value. You can also use it for getting voltages to say, let me make sure this resistor is not going over its power limit, such as if this is a 0.25 watt resistor, one of the most common types. So you have V equals IR, and then P equals VI. You don't even need the resistor. You can calculate how much power is voltage and current, and you know whether there's too much power going through here for any resistor that you own. Now, you can do the loop the other way. What if we do the loop this way? Don't change the arrows. Let's say we're doing the loop backwards with the arrows as they are. Well, V1 is positive, but we're going backwards. Your voltages here that you have written down, whether you know them or not, the positive and negative is based on the current direction. If you're going against the arrow, you negate whatever it is. So you have negative V1, because we're going this way, so we're starting here. Across the battery is negative V1 plus, now we'll go over here, and we have a negative 3 volts. Negative V3 is minus V3, but we have to negate it again because we're going backwards. So we do negative V3, and then plus. Again, we're going backwards across the resistor. Now, a resistor is going to drop voltage no matter which direction you go. If we actually reverse the current and take the LED out because it's going to block the current, but pretend the current flows in the other direction, you'll still get the same voltage drop. But this is for circuit analysis. We're not actually flipping the current. We're just drawing it backwards because we can. There are situations where you want to do this. Uncommon ones, but they exist. So you can go across it, but we're going backwards. It's the arrows. The arrows determine, the current arrows we've drawn determine if we're going backwards. So negative V2 equals 0. So it's the same thing we had before. V1 minus V3 minus V2 all added, but we've negated all of them because we've gone against the arrows. So now we simplify. This is just negative V1 plus minus minus V3. Well, minus and minus is plus, plus and plus is plus. So it's plus V3. And again, it's plus a minus minus V2. Minus and minus makes plus. Plus and plus is plus. So it's just plus V2 equals 0. And you can see this is what we had before, because before we had V1 minus V2 minus V3 equals 0. What if you multiply negative 1 into all of these? Negative V1 becomes V1, V3 becomes negative V3, V2 becomes negative V2. It's the same equation. So that's why it's so easy. Step 1, draw the arrows. Don't worry about which way you draw it. If you draw it right, there you go. If you draw it wrong, you'll get negative currents, but you'll get the right answer. You just have to flip the current arrows. So draw the current arrows, then in that direction. So if the current's going from negative to positive on a power source, you have a plus voltage. You always have a negative voltage on a resistor. And then, of course, you have to have your current going plus to minus on the LED, but an LED drops voltage as you go across it. So what if we had a more complex circuit? So here we have a circuit that does a great job of generating heat. Just 4 resistors and a power source. Now, what does it mean, a closed loop here? Well, let's say we start at the negative end of the battery. If you go up here and through here, these 2 resistors and around, that's a closed loop. If you start again and go down this time, that's another closed loop. If you remember your algebra, you'll hear things like, I have 2 equations and 2 unknowns. That's how you know you can solve for the values. So if you know, let's say for whatever reason, you know the voltages across these 2 resistors and this one, then you need 2 equations because you have 2 unknowns. So you do that loop and you get 1 equation, this loop using different values, and you get another equation, and now you can just use algebra to find both of these voltages. But you can also do other loops. You can do a loop here, ignoring the power source entirely. You can do it twice. You could start at the battery, you could go here, and around, and here, and back through the battery, and around this way, and back out, and back to there, if you wanted. As long as you don't double back on yourself, don't reverse, just keep tracing a line through junctions, and end up where you started. That's it. So we start here, we can go, you see I'm not backing up. You know, I'm changing direction, but I'm going around a loop to do it. And we end up back at the same spot. The math will work. It'll work perfectly fine. Just remember, draw your arrows. It doesn't matter which way the arrows face, you'll get negative currents and know that you need to flip the arrows once you do all your math and check it. But remember, when you're not at a junction, the current has to stay the same value, same direction. So you couldn't have here, then here, then here. Starting from a junction to a junction, the arrows must keep pointing the same way. I could flip this if I wanted. That's obviously wrong, and if I do my math, whatever I calculate for this current will be negative. But they're consistent. From this junction to this junction, they're facing the same way. That's all you need. So why does this work? Let's fix the arrows first. And let's label our voltages. V2, V3, V4, V5. Now, based on the arrows, remember, resistors drop voltage either way. So if we're going this way across a resistor, of course, it's a drop. A drop, a drop, a drop. And over here, if we have V1, for the battery, the current is going, our arrow is going from negative to positive, so that's positive V1. But we're not going to use V1. We're going to do this loop. So let's start here, go around, and end there. So first we are going in the direction of the arrow. That means we take whatever we have written, minus V2. We are again going in the direction of the arrow, minus V3. Now we're going here, we're going backwards across the arrow. We're going against the arrow. So whatever we have here, we have to negate it and then add it in, or subtract it. It's the same thing. So instead of adding, we subtract negative V5. Minus V5 is plus V5. Again, we're going backwards across the arrow. So negative V4 negated is plus V4. And now we're back at the start. We could go around, we could do whatever we want. That's good enough. Equals 0. So we have two negatives and two positives. Just move the V2 and V3 over. What do we get? V5 plus V4 equals V2 plus V3. I just moved those over to where the 0 is. Does that make sense? It sure does. V5 plus V4 is this. V2 plus V3 is this. Now, this junction is connected to the positive terminal of the battery. This junction is connected to the negative. It makes sense, trust me, that you have to have the same voltage drop across both. So whatever these values are, they end up being the same drop because you're going from, let's say, plus 5 volts to 0 volts through both these paths. As long as you remember to negate when you go backwards to the arrow, it's super simple. And that's all the voltage law is. Step 1, have your circuit. Step 2, draw arrows for all the currents. Doesn't matter which way, just try and make it make sense to you. Step 3, for each component that you care about, that you're going to do a loop over, label whether it's a voltage increase or decrease based on that arrow's direction. Step 4, trace your loops, write down the values. If you're going with an arrow, write down the value you had. If you are going against an arrow, write down the negative of that value. Add them all together, equals 0, then do whatever math you need. That's the entirety of the voltage law. The current law is actually super quick and easy to explain. The voltage law applied with loops. The current law applies at junctions. Anywhere you have more than 2 wires connecting, this is not a junction because it's just going from one thing to another. A junction is where more than 2 things connect. So we have 2 junctions. So let's just take this junction. Let's label our currents. Again, it doesn't matter which direction you do it. Let's do it that way, that way, that way. Remember, when it's not a junction, it has to be the same. So this one has to go in here. Furthermore, this one backing up has to be the same. This one backing up has to be the same. And then through this wire is the same wire as this wire. There's no junction, so it has to go that way. And there you go. Let's label them. This one is I1, I2, I3. So this over here is also I3 because it's the same wire, same current. This one is also I2. And this one is also I1, which over here is also I1. The current law looks just like the voltage law. At a junction, sum the currents, and it equals 0. Now, you have to pick numbers here. Do you decide if a current is going in, is that negative, or if a current out is going negative? Doesn't matter. Whichever one you want, whichever one floats your boat, all you have to do is be consistent. Let's say going in is negative and going out is positive. I3 is going in, so negative I3. I2 is going in, so negative I2. I1 is going out, so plus I1 equals 0. Let's add it over. The I3 and I2 over to the 0 side, and we get I1 equals I3 plus I2. Now, it makes intuitive sense. You have to have the same amount of current going in as you have coming out, because otherwise current is going into or out of thin air. If you have more electrons going in than coming out, they have to be spraying out into the air. If you have fewer electrons going in than coming out, if more are coming out, then they've got to be sucked out of the air. They have to come from somewhere. They don't just pop in and out of existence. So it makes sense that this current equals this current, which means you can even not worry about the negatives. Instead of doing it with positives and negatives equals 0, remember, if you just add the negatives over, you get the one on the one side and the other on the other. So let's just say write down all of the ones going in the same direction. All of the ones going in. I3 plus I2 are going in. I1 is going out. Just equate in and out. There you go. If we had labeled out as negative, then that would be negative I1 over here. We'd add it over and we get this. What about over here? So we could say, we decided, we got to be consistent, that in is negative. So we have negative I1 plus I2 plus I3. I1 is going in, I2 and I3 are going out. Or we can do the same thing here. First, write down all the ones that are going in. Well, I1 is going in, then I2 and I3 are going out, equals I2 plus I3. And of course it's the same thing, because this current has to be the same. This current, you've got to have in and out be equal. And that's all there is to the current law. There's nothing else to be shown. So when we were saying things like we have two equations and two unknowns, or we have two unknowns, let's find two equations, this is just another equation you can do. You can do loops with voltages, and you can do junctions with currents that are involving the things that you're calculating the voltage over. That just gives you more equations that you can use to find more unknown values with linear algebra. But that's the current law. The voltage law just says any loop, you have a net zero voltage. You have your power, then you have your drops of things happening equal zero. Your current law just says you have as much going in as you have coming out. It's almost like the conservation laws. So it took a while to show the math, but that was just showing you how it works. Using it is very simple. Add them up equals zero. And remember, if you get negative currents, just flip the arrows. And now you have everything you need to know to work with and maintain simple circuits. There will be plenty more math to come on specialized and specific circumstances. But these are all the general laws. These are the things that you need to keep in your brain. These are the things that you will use practically every day that you're doing electronics in some way, even if you're just doing it intuitively. You don't need to think about some law to realize current in must equal current out at a junction. That is basically intuitive. But every time you use that intuition, that base knowledge, you're using Kirchhoff's current law. So that's about it. I will now use these laws in a future video to demonstrate how you calculate equivalent resistance if you have resistors in series or parallel. But until then, be seeing you.